All right, so happy to see you all here. So just, a couple of words. We are very happy to have our guest speakers today, Ahmed and Thomas, and we are very excited about the topics that we'll get to see today. A couple of, logistics and organizational before we start. We typically have the chat open for any kind of questions and thoughts during the presentation part. And we can address these questions as soon as possible. You saw already that you have the possibility to turn on your camera and mic. You can also then ask your questions. We encourage that. We have a live Q&A discussions after the presentations. So we keep it casual and let's have a nice meetup today. Without delaying too much, I would like to pass the ball to Lindsay for the usual brief. Lindsay, stage is yours.
Okay, let me just see if sharing is going to work for me here. Fingers crossed, and there it goes. All right, okay. So just to make sure, okay, so welcome one and all to xeokit meetup number 5, the Spotlight Edition. And just to make sure we're on the same meeting here, just to make sure, let me just quickly define what the xeokit SDK is. So this is, can you see my screen? Is it sharing? Yep. So this is a JavaScript SDK for visualizing large AEC models in the browser, and it's built from the ground up for this purpose and for visualizing particularly like GIS datasets. It is natively double precision, and it's geared to visualizing really large datasets in the browser. It's open source. And that's pretty much defines it. Yep, and it's a foundation for building your own custom model viewers and enterprise digital twin platforms. So I've got today an update with a few new things in our xeokit ecosystem, starting with reorganization of our repositories. So we've got the main repository here, which contains the SDK itself, and we have factored out the examples into their own repository here, so that you don't have to actually check out the examples every time you clone the repository, because we've got some pretty big models in here. So we've just trimmed down the SDK to the actual code, so that if it's an npm dependency, you're not dragging in megabytes of BIM models. We've also deprecated a lot of dependencies. We've also removed a lot of deprecated npm dependencies from xeokit SDKs to minimize that vulnerability surface area. Keep things really lean, stay in control. But the juicy bits, I wanted to just introduce you today are the xeokit data engine. So as you may already know, we provide an optimized data format here called xkt, which is compressed for optimized. It optimizes your BIM models and whatever for web applications. And so we have this data engine here, which converts various source formats into our web optimized formats without loss of the metadata provided within these formats. So we can convert things like Revit files and IFC and STEP and things like that. And as a component within the data engine is this component here, xeoRET, which takes native Revit files and converts them directly into open formats that are ready for the web, without depending on Autodesk infrastructure or forcing everything through IFC first. Because, as you know, Revit is not a natively IFC platform. It's it's not actually built around IFC. So zero Revit means the preservation of the source data, more flexibility for developers, and greater control over where and how BIM is processed. So that's zero XeoMeetup.
And it's fully independent from Autodesk, right?
Yes. And following on from that, we also have a new tree view component. So one of the philosophies of xeokit is is customizability, the ability to extend it, customize it as you need it. And so we also have a new tree view plugin, which is deeply customizable so that you can so rather than relying on a fixed BIM tree, developers can generate their own navigation structures by instances, families, levels, or any other hierarchy, and connect them directly to 3D selection, visibility, and property inspection. So this is an example of how xeokit's semantic data model enables highly customized BIM user experiences beyond traditional viewers. So we're not just coupled to IFC. And so the key takeaway from this is metadata first UI development using xeoIVT's extracted semantic structure to build completely custom navigation and property interfaces rather than relying on a one-size-fits-all tree component. And last but not least, to our CX converter CLI tool, which converts IFC files into GLTF files, which we can then convert into XKT files. We've added a new feature called extract out a shape. And this basically reduces the size of IFC-derived GLB models by exporting mainly the surfaces that are visible from the outside. So using this feature, you can create a lower level of detail representation of your models. So, yep, I'll just leave it at that. There's 3 or 4 new features from us.
Thank you, Lindsay. That's very good transition also into our one of the main topics for today is how GIS applications integrate with BIM. So there are different ways, and this new experimental feature is it's basically the other way around, not bringing GIS context into IFC models, but basically bringing IFC models into GIS context by reducing the IFC models only to what's relevant for the GIS view in 3D. So yeah, give it a try, and we'll be happy to get your feedback. Same is valid also for all the other new features. And xeokit data engine, of course, the data processing unit of xeokit. So feel free to drop us a line in the chat. If you have any questions or any thoughts, we'd be happy to discuss. And I guess now we can move on to the next topic. And our guest speaker today, Ahmed from LGV Hamburg. I don't know exactly how to say it in English. Representing also the Masterportal and how it's integrated with xeokit. So, Ahmed, are you ready? Yeah. Yep, you're ready to go.
All right. Yeah. So, hello everyone. Today I will show you how xeokit and IfcOpenShell are used in Hamburg for digital city planning, also with our open source Masterportal and urban data platform. My name is Ahmed Salem from the State Agency for Geoinformation and Surveying, LGV, in Hamburg. So I work in the office, the BIM coordination office, BIM Leitstelle, and my focus is mainly on infrastructure modeling, BIM GIS integration, and urban digital twins. So the BIM coordination office has the central goal of implementing BIM in the city of Hamburg and, of course, in LGV. We work also on BIM-based modeling for buildings and infrastructure. We provide project support and advice for teams to apply BIM in practice. We also run lots of research projects and, of course, take part in national committees and develop standards together with the organization BIM Hamburg. We work also with measurements like for existing structure with tachymeters as an instance. We collect these data points, lines, and import it in CAD software prepared according to the Hamburg standardization catalog. And then we proceed with modeling this data from the measured data. We first create the digital terrain model from the surveyed points and edges. And then we use the georeference data and model them on top of terrain models like for trees, street furniture, retained wall, and so on. But we have also the so-called Hamburg standard data packages in which we have standardized data like ALKIS or terrain models in form of GeoTIFF photos and also the 3D city model in form of CityGML. And we proceed with each data set is imported, prepared in CAD software, and turn them into 3D models. Today, I would like to present you a project connected to urban twins, which we were part of. We integrated in this project the BIM methodology to bring together the benefits of BIM and urban digital twins. First, the project itself, Connected to Urban Twins, is the joint project between Hamburg, Leipzig, and Munich. Together, we developed the urban digital twins as a foundation for the integrated urban development. And the project covers a lot of areas like urban data platforms, citizen participation, experimental urban research, knowledge transfer, innovative use cases. But we don't have a single urban digital twin for the entire cities. Urban digital twins are modular. So we assemble geoinformation, thematic data, analysis, applications, and geospatial twin for each specific urban challenge. And the Urban Data Platform Hamburg, UDP, is the city's central data infrastructure. So it connects and provides mainly public urban data through open interfaces like OGC API features and processes, or web feature services and web map service, WVFS and WMS. And the platform itself includes more than 600 data sets organized by theme or by authority, and it's widely used across the city of Hamburg. Internal application, but also external apps are built on this data and using it for the different topics that need it. The Masterportal is the open source web GIS tool, so it's released under MIT license, and it's used for visualizing and editing these spatial data. So it's like the front end of the urban data platform, the infrastructure. And it was developed by public administration partners across Germany. It's here in the map, you can see where it is used across Germany. One example usage of the Masterportal is the Geoportal of Hamburg. So here users can search for data in Hamburg from the urban data platform, also add thematic layers and use them to work with it, or either directly in the map or use the information in their specific need. I would like to show you two use cases from the project Connected Urban Twins, in which we implemented the BIM methodology. So the first one was the BIM-based collaboration platform for major events. And in this project, it's like a collaboration platform. It supports the collaboration urban digital twins using the BIM methodology. For example, the BIM models for temporary construction during large events. So we have events, BIM, and DPAS. DPAS is the digital participation system in Germany, and all together form the collaboration platform. So we try to form like work areas, and the three main areas were the event management, the BIM viewer, and IFC storage, from which I would like to show the BIM viewer mainly. But we worked in all three topics in parallel because we had to develop the whole project at once. But for today, it's relevant maybe to show you this part, which we aimed also to make it modular, consists of three main modules. Like the first module is the Masterportal, in which we integrated BIM viewer using the xeokit SDK. And the second module is the Urban Data Platform, which we use to store the IFC files, the documents, and the photos. And the final modules is DPAS, which we used it for the communication. And all these modules form the collaborative platform, and we try to make it very easy for people who are not familiar with BIM methodology. So it's like for everyone to use. And I would like to show how it looks like. So this, we used use case UFF Fan Zone 2024. We had data from the organizers, and here you can see some information about the event. And then you would go further, and you see on the left side the map of the city and the event itself, and on the right side the BIM viewer using the xeokit SDK, in which you can visualize the IFC model. And you can also see the annotation using the 3D annotation feature in the xeokit SDK. And these annotation are like the issues that the stakeholder are communicating through. So you can either make an annotation on the left side in the map or on the right side in the 3D model according to the needs. And here is a scenario where a user creates a contribution. So the police measures the escape route, emergency escape route, and find it's not wide enough. Then they can create an issue by writing brief text and description and describing what's the problem, and then specifying which category this issue is. We had some issues or some categories to make these issues, and then they place these 3D annotations in the model. So they zoom into the place where it is and place this annotation, and then save the issue, and it will be visible for our stakeholders to communicate through it. And it's like communicating with a very easy way, convenient way through the DPAS, the digital participation system, using the BIM model. And of course, all the issues can be visualized in a dashboard, and you can see all the across the stakeholders. They can see the information and the questions and so on. The second topic we also implemented in the Connected Urban Twins project focused on the automating BIM modeling. So we found out modeling-based data is very time-consuming, and source data is not always available as an IFC or IFC-compatible format. And GIS and BIM are somehow different in data structure, so conversion might be often required multiple software and tools. We aim to provide the geospatial data such as city models, street trees, and digital terrain models, and so on, as an IFC format. So the user can select a boundary and the 2D map and then generate IFC model on the fly based on this data without saving it as an IFC. So this happens when the user creates it. We had the components. We presented the Urban Data Platform, also the Masterportal as a component, and the BIM viewer with using xeokit SDK, and the workflows which we created using IfcOpenShell. And the whole components we called our product the BIM Fabric Hamburg. The BIM Fabric Hamburg, the first step was to also develop the BIM viewer more, and we implemented it in the Masterportal itself. And as you can see here, you can open the IFC file directly in the Masterportal. So we made it integrated BIM view on the right side, and here it's loading the IFC directly. But we also added the possibility to open xeokit files and GLTF files, and of course you can see the information on the right side. So this was the first step to be able to open IFC files in Masterportal itself. And the second step was to create the workflows. But what is a workflow? The workflow describes this automated processing of data sets. So on the left side, you have different data sets, CDGML or other data sets, and it passes through automatic workflows. And on the right side, you get an IFC model. We would like to show how the BIM Fabric Hamburg looks like. So you have here on the right side the different workflows which we created, and you have the Masterportal as a whole application, and on the left side the BIM viewer. The user can select boundary and then insert some information what they need in the model, and also they can choose how it looks like, which level of detail, and then they press our IFC generate, and it processes on the fly, so it's not saved anywhere. It's created when the user clicks on generate, and of course they can proceed and create a city model. So they also it's CDGML. They insert the information they need. Also choose which LOD this is and click IFC generate, and it also happens on the minute or on the second the user press on generate. And they can go further also for the digital terrain model, and the result would be a collection of IFC models that are needed for planning or for whatever use in the digital twin. And of course, you have the information that were part of the GIS data. We have them in IFC as PSATs. It looks like it's very simple in front end. So you have the user has some clicks to do it, then the IFC model is generated, but it's very complex on the background. So we have on the left side the Masterportal with the BIM Fabric Hamburg, and the user sends the requests which pass through the OGC API or API processes, and it sends this request to the server, and there we have IfcOpenShell and our workflows. They take the data from the source of it, which is OGC API features, but also other sources like CTGML files and so on. And then the model is modeled on the fly and then sent back to the front end, which the user can either visualize directly as in the video or also download it. We used for the modeling like native IFC concepts, and it was possible with IfcOpenShell. So we model with these concepts. We don't export what we model with as a native format, but we also worked together with Thomas Krijnen and created like a library which abstract these methods in IfcOpenShell. So to have it like we call it generic modeling, and the library itself is called IFC Factory, which provide simple forms so you can model boxes, cylinders, spheres, and so on, and use some operations with a very abstracted way to create the models as an IFC native models and use it to form the workflows. And this is also available as a library itself to use it apart from the project. We also try to make it modular in front end, so you can see with some configurations, you make the front end the workflow without making some code again. And lastly, we want also to provide it as an OGC API processes, or you can create the models without front end at all, so you can implement it directly in the software. And so it's very modular, and we published all the libraries, so you can decide which library is for which application, use for BIM Fabric Core for the workflows, or the IFC Factory for modeling, or API for without user interface, or use the BIM Fabric UI as a complete package with the xeokit integrated inside it. So we have the repetitive process are simplified, standardized. The use of BIM within Hamburg is expanded, and we have one application for everyone. Next steps. So we want to further develop the BIM Fabric Hamburg in a modular way. We want to add additional data sets, and of course, we want to add different coordinate system to have also the transformation on the fly to be able to have more than one coordinate system, so that to transform the BIM Fabric Hamburg into BIM Fabric Deutschland. I reached the end of the presentation. Thank you for attention, and I'm ready for your questions.
Thank you, Ahmed. This was really, really insightful. I was especially happy to see, during World Cup, we saw xeokit being part of the European Cup 2 years ago, in some way, together with DPAS and BIM Fabric. It's really nice to see. For me personally, a bit unexpected use case, but actually after you presented, it totally makes sense. So yeah, very exciting. And I guess long live open source. So we have gathered today all the right participants: xeokit, the Masterportal, and IfcOpenShell, represented by Thomas. So guys, please feel free to add your questions as they come in the chat, or you can just unmute now during the breaks and ask directly. 1, 2, 3. And I guess, yes, Thomas, we can move on with your part. Very happy to have you both here. And yeah, stage is yours, Thomas.
Yeah, thanks. Can you hear me okay?
Yes.
Thanks for the invite, and thanks for the 2 previous presentations. Really nice to see. So really quickly about me, or what I do in my day-to-day life. I basically do consultancy around open standards. Typically that's IFC, and more often than not, it also has a geometric component to it, because because I think that's where a lot of the challenges are in our sector and in the neighboring disciplines. I think that's also apparent from Ahmed's presentation, and that's also why it's so essential to have good viewers, because we're all visual people. So there's a lot of work on voxelization for spatial and geometric analysis. I also do quite some consultancy for Building Smart, which is the standardization organization behind IFC. So for example, the validation toolkit that looks at the validity and conformance of IFC models. They also help with IFC 4.3 and 4.4 developments, and also other geometric simplifications. Here in the top left is very similar to what Lindsay was talking about here on the building level, isolating the outer surface, or on a spatial level, doing kind of aggregations to come to higher order areas or zones in the building model. Because typically the architectural model, let's say the individual spaces on the left, what's physically bounded. But if you talk to the real estate people, they really want to know higher order things like total rentable surface area or net or gross volumes for in what configuration, and the kind of specific joining over only the non-load bearing partition walls, because these are the things that a renter could easily move themselves. That was also specifically implemented. So it's not just an arbitrary Boolean union, but it kind of blends over everything that's non-load bearing to come to the representation in the bottom right. And then I always include this slide. So for people that don't know what IFC is, if there's questions, by the way, in the chat, please just shout, because I probably wouldn't see it. But sure. IFC is this very typical mechanism to represent the building as a set of products, and each of these products typically have their own solid volume representation, which also shows the kind of the complexity here in the top left. It looks so straightforward. Just give me the outer shell of the building, but it spans across all these elements. So that's also the complexity there. And then, I really look at us open source developers as creating this blanket or patchwork of all our own little modules. And you can talk about the aesthetics of it. So everything will look a little bit different. Everything will feel a little bit different. And maybe you don't like that, right? Maybe you just want this kind of corporate feel of, every application looking the same. And maybe you wouldn't get that as much with open source software. But I think it's also really empowering, that if you don't like a particular piece of your quilt, you can take it out and substitute it with something else that's a better match with your workflow. And that's also, I think, why it really enables to move from just being a passive consumer of software to really taking ownership of your workflows and your design methodologies or your specific analysis questions or whatever. So I think it's really empowering. And then, this is the opposite, this kind of polished experience. It looks very neat, but ultimately doesn't give you a lot of freedom to adapt it to your needs. So in IfcOpenShell, we took the LGPL license as our open source software license, because we really believe that it is kind of a foundation that people can build upon. And the LGPL license, basically, I would summarize it as you can use it however you want in commercial or non-commercial products. But if you improve IfcOpenShell itself, if you make that foundation itself better, then you need to contribute that back. And I think that really works well, because IFC typically isn't, let's say, the value proposition of the company. They operate at a different level. IFC is that foundation for information exchange. So it also doesn't really collide with, let's say, the business interests. And I think that works quite well. I think IfcOpenShell over time has grown into quite an impressive set of tools. For testing, clash detection, but also generation of models. Ahmed showed something, but there is also, for example, IFC patch, where you can, I don't know, apply certain transformations to your data in a pre-encoded way, or conversions, ECF. And of course, recently, this picture is too old, but we also have Bonsai, previously called Blender Bin, built on top of IfcOpenShell to really be this human-centric authoring platform. Now, my initial mission is really to automate the boring parts away in our jobs. This has kind of been a red line for 15 years in what I see, that a lot of workflows, a lot of cool ideas, a lot of initiatives kind of break down really at the simple things, you know. That one of the earliest things that people came to me for in terms of use cases was, I just need 2D elevation drawings of every wall in the model. And people were literally really doing that by hand. And it's error prone and time consuming. And these are really the things where I think IfcOpenShell shines because of its extensive geometry, its extensive APIs. It can really, in a couple of lines of code now, provide you that kind of tooling. Something that I'm really quite proud of is the amount of contributors we have. So, what is this again? So the orange thing here is that's probably me. That's my contributions to the project over time. But then over time, other people joined, and I think blue, that's probably Dion Mold starting to work on Blender Bin, and there is other influential people now in the community that really contribute tremendous knowledge and contributions. In terms of our software languages, it's mostly C++ and Python, and it's no surprise, I think, that these graphs are a little bit similar, right? With the amount of contributors increasing, so every contributor here is a unique color. You also see that Python kind of surpasses C++ now in lines of code. Because it's just a more accessible language. Now, okay, what I actually wanted to talk about today is how xeokit and I recently collaborated on bringing IfcOpenShell, let's say, more closer into this xeokit viewer ecosystem, and the opportunities for improvement that there still are. So IfcOpenShell is quite a modular code base. It's quite old, 15 years or something, so it's not always the cleanest, but in essence it's quite modular. We have, let's say, a data model foundation, schemas on top of that, geometry libraries on top of that, serializers, Python bindings, higher level APIs. And then, let's say, application areas such as IfcConvert or Bonsai, drew them on the left. So it's quite modular in code. Oh yeah, and then, for example, two of these serializers, after our collaboration, are also binary GLTF with the right spatial hierarchy as xeokit expects it, and the JSON extract of the properties and the semantics. So this can be on the back end nicely fed into this XKT format. I don't think we did a lot of work on this afterwards, but in theory these things are sitting here now, and we could look at further optimizing them. But these are two examples of these serializers that take the IFC data and write it out in a different form, either geometrically or the semantics. And we also have client-side loading. And this is a little bit where there are still things to improve, because, like I said, the code base itself is quite modular, but but the applications, as we distribute them, are really quite monolithic. So for example, IfcConvert, you just download as a, I don't know what it is, 30 megabyte executable, which is really nice because it's portable. You don't need an installer. You can just run it from your USB drive if you want. This is nice for desktop applications, but it really starts to hurt a bit if you need to download 30 megabytes before you can start interacting with your web application. So it's this is let's see what you need to run IfcConvert. You don't need the Python bindings or the high-level API then, but you need all the plumbing and geometry processing. If you want to have the Python binding, you need to have this whole stack on the right. Now, and if you want to use this xeokit client-side loader, that means you need to load Pyodide, which is a browser runtime of Python, WebAssembly implementation of Python that can then import this monolithic module. And yeah, that's really megabytes later, and hence seconds later, you can start doing things. That's really a bit painful. So I want to talk to you about some of the changes we have been working on. And on the top right, you see IfcOpenShell 0.9. That's not released yet, but just some things that are coming. So maybe from the bottom up, which is actually not relevant for this use case here, but we have a completely new storage model based on RocksDB, which is something originated from Facebook, a key value store, which means you can really offload all your memory usage to disk and have real-time writes to your database, as opposed to the old import-export workflow of IFC. So this would work really nicely in Bonsai. You can just, yeah, you don't have this export step anymore. You just incrementally directly write your changes to the database on disk. Something else is that so here, what you see here is that every combination of schema and geometry library. So IfcOpenShell actually has multiple geometry libraries that we depend on for the geometry interpretation. And previously, every schema and geometry library combination thereof was a separate module. And what we introduced is a thin taxonomy layer that we call geometry mapping. Okay, I see there's a lot of IFC2x3 here, but that doesn't matter. So basically, we unify the schema differences. We eliminate redundancies. So for example, in IFC, a tessellated face set or a faceted boundary representation, it's basically the same thing encoded in a different way. And there is some IFC specific geometric forms, such as an I-shape profile definition that we translate here to a composite curve. And that means that one layer higher at the geometry libraries themselves, they can be fully agnostic of the schema. So we don't need this full matrix anymore, but these operate on a more abstract level, more abstract from IFC directly. And we also have more of them now. So OpenCascade is really nice, but also really quite heavy. Seagull is a bit academic. And for example, Manifold is really much more modern and also correct. And then we also have pass-through, which works nicely for the IFC4 reference view models. It just basically doesn't do anything except just passing the data through. So yeah, that is really a nice enabler for this kind of, this taxonomy layer simplifies the amount of effort required to implement geometric support. Now, we also will provide a WebAssembly binding directly. So in a xeokit kind of use case, you wouldn't need this Pyodide well, you could even call it an emulator to emulate this whole Python ecosystem. But you can cut that out directly and from JavaScript immediately talk to the WebAssembly compilation of the IfcOpenShell C++ code. That's the Google Summer of Code project. At the same time, we are, and that's really the lovely time we're living in now with AI, this high-level API that's currently in Python. We can just transpile that to C++. We have hundreds and hundreds of test cases that cover that API. So we can, bring that one level down actually to C++, which means it will also be available as this WebAssembly module, because that was typically in the past a big argument that's still shipping this Pyodide environment, because well, all the interesting functionality, the IDS checking, the BCF writing, all these kind of things were written in Python, so hence still required Pyodide in the browser. So I think that's really quite interesting. And then very fundamentally, here I drew this thick line over all our modules. I said code is modular, but deployment is not. And that's also changed now in 0.9, where everything basically is a plugin now that you can load on demand. So if you load an IFC model and you encounter, I don't know, advanced BREPs with NURB surfaces, at that time, you bring in OpenCascade to resolve that. And otherwise, you can stick to the much lighter, faster to load geometry libraries. So on all fronts, I think this browser-based experience of using IfcOpenShell has seen some quite nice improvements. And here I sketched that a bit. So what do all these geometry libraries support? So for example, extrusions are supported across the board because it's trivial, but quite a few things are still OpenCascade only, such as the advanced BREP with NURB surfaces, but also there are some quite advanced sweeps where you have both a surface and a curve, where the surface defines the orientation and the curve defines the defines the actual route over that surface to sweep. And these kind of things you wouldn't want to re-implement in a new library because there's so many caveats there. And then there is also things that the mapping library itself already solves, such as some of the primitives or the IFC 4.3 specific infrastructure sweeps. So I think that's it. I'm really quite happy with that after 15 years we're still able to shuffle things around and also provide more fundamental improvements. And I think they're really quite relevant to the community here working on web-based visualization. Thanks. Any questions?
Thank you very much, Thomas. It looks really nice. As you mentioned, after 15 years, you're still innovating as if you started yesterday, more or less.
Thanks.
Looking at the chat, I don't see exactly any questions, but I have a couple of questions for you guys. It's basically the same question for both of you, but maybe we start with Thomas. How can we use the serializer that you mentioned for the GOB and JSON?
Like I said, I think it would be nice if somebody either in the community or us spends more time on figuring these things out. So in principle, from my side, it's quite straightforward. You just run IFC convert or Python to convert the data.
So you just
run
IFC convert.
And then from what I understood, there is a converter on your end that takes these two inputs and writes out an XAT. And we tested that. But that was about it. I think we didn't really, let's say, really take it for a test drive. And so I think that's still interesting tasks that could be picked up if there is interest.
So the entry point would be IFC convert for this one.
Yeah, either IFC convert or the Python bindings. The Python bindings have the advantage that you only need to open the file once, because you can keep the file in memory and then process it multiple times. If you use IFC convert, because we don't really spend a lot of time on the command line interface, you can only write one export at a time, so that you need to run IFC convert twice, which might be a little bit of an overhead, even though the parse time isn't typically the bottleneck. It's more the geometry interpretation typically.
All right, great, thanks. Ahmed, the question also to you. Maybe I've missed it, but how can someone use the Masterportal?
Yeah, so we published the whole packages. We have, as I showed, the 4 modules, and some of them for the backend and for the front end, and we have an open code, like the Masterportal with the BIM viewer combined in another repository. So we have the Masterportal itself as it was in the repository, but now we call the new repository BIM Portal Hamburg, and you find in it the Masterportal and the BIM viewer as an add-on integrated, and so the user can download the package and run it with npm and or host it on server, so locally or on server, and then they can, of course, then use the BIM Fabric Hamburg as an add-on extension to run the automated geometry processing or modeling process, but they could use it without backend, only at the front end for viewing the models.
So basically the backend part would be a separate thing.
Yeah, they are modular, so you can use it as also Thomas showed. We try to make modules so you can use it as BIM viewer with a Masterportal, integrating the 2D maps and so on, and using the data. And if you would like to generate models, then you use the BIM Fabric as inside it as well. So in open code, you find the repository for the BIM Portal Hamburg.
Okay, so I guess we can send some links.
Yeah.
In the feedback email. Yes, great.
Yeah, I could send you the links because this is for the front end and also for the back end. We have 2 or 3 other libraries components also on open code, and I send you the links.
Perfect. Great. Thank you, Ahmed. Okay, guys. Any thoughts looking around? Any questions? I have one quite technical and geeky one for Thomas. But just looking at everyone. Okay, I'll just go ahead. So, Thomas, you mentioned manifold as a geometry kernel that you're now using also somehow in parallel to OpenCascade. And I got a partial feeling that OpenCascade is still like the main base because it covers all the different geometry types and operations. But you mentioned that manifold is actually more modern. So how does it really compare? Is it also fully open source? And this is maybe the second part of the question, but how do you see things?
Yeah, it's fully it's also fully open source. It originated from somebody who at that time worked for Google, had this 20% project or something where he was able to spend some time on it, sponsored by the company. And over time, I think it has seen quite a rapid adoption in various other open source libraries, because it has a quite nice combination of, like I said, modern, which means lightweight, a lot of bindings or targets such as WebAssembly or scripting languages, but also correctness. It's also in that sense quite academic, or maybe not academic in the bad way, but in the good way, that it really explores novel ideas how to solve that, because geometry simply is complex. And then how these things interact, I think there's a bit of an interesting dynamic in how IFC models are exchanged, that they're actually becoming simpler and simpler and more explicit. So in IFC 2x3, this MVD, that's the let's say the configuration that exporters were intended to use, was called coordination view, which had a pretty nice middle ground between expressiveness and simplicity. So you would have still extrusions, and then parametric openings for windows. And then with IFC4, this became much more explicit, and basically, because it ultimately also wasn't completely reliable, and so the data got much more explicit, which, it took a long time for IfcOpenShell to adapt to that, because OpenCascade is really has a painful overhead for these explicit meshes, because for every let's say triangle, it will store a face, and then for every edge of the triangle, it will also store a curve, all in quite a few indirections, as we say in computer science, because that edge curve wouldn't necessarily have to be a straight line. It could also be curved. So all these kind of permutations and support for complex shapes came with a lot of indirections. Also, for example, an edge could actually have the same vertex, because it could be a fully circular edge. So everything is like a container aggregating lower level topological entities with potentially geometry, which is reference counted. So it's really there is an immense Christmas tree of objects stored in memory to store a single point or a single triangle or whatever, and it took quite some time to adapt to that. So then, answering the question, it depends how you look at it. So I would say OpenCascade is still let's say the basis if you look at the breadth of the IFC specification, because it supports a lot. But if you actually see how we invoke it, it comes, let's say, last in a series of attempts. We just, let's say, first try the simplest, most lightweight geometry library to interpret. If it fails, then finally we fall back to OpenCascade. So it relates to how IFC data geometrically became more and more explicit, at least in the mainstream data. There is still, of course, advanced use cases where this parametric data is being used. And then it's a bit of a paradox that it has the highest breadth in support, but comes last in the execution.
Basically more stability through redundancy, in the
exactly.
fallback.
And
Yeah.
if that's a nice way to phrase it. And it also has other opportunities that we don't really leverage yet, but we could also run the conversion multiple times through all these engines. Maybe even add a voxelized one, because there you're kind of 100% sure that a Boolean operation would be robust, because it's literally just flipping the bits of the voxels. And then within this error bound, you could check if they all agree, and then you decide, what do you do if they do not agree? Do you pick the largest one and think it's best, or do you I don't know. That's still things to explore. But if performance is not the foremost concern, but correctness, then this multiple set of implementations indeed also still has other possibilities for cross-referencing.
Very interesting. Thank you very much, Thomas. So looking at the time, guys, I would say we can wrap it up with our official part. We'll stay a bit longer if there are any last-minute questions. Thank you very much, everyone, for attending our xeoMeetup. Looking forward to see you again next time. And thank you very much to our guests, Ahmed and Thomas, for being with us today and sharing their experience. So yes, have a great day, enjoy, and see you next time.
Thanks all.
Thank you very much.